This is Project Altitude, a series where I try to build rockets that will go to higher altitudes than the rocket before it. In the previous episode, I tried to perfect my rocket design, but it didn't go all that great. I ended up with a rocket design that was worse than the one that I started with. If you haven't seen the last video, go check it out. But basically at the end what happened was the rocket flew off course and flew every which way. In the last video I said that I had a few theories for why the rocket messed up. I believe that the reason that the rocket flew off course was because that the pieces that I printed to hold it together, the supports on the outside, were not aerodynamic. I planned to improve this design by designing connectors that would go on the inside of the rocket instead of on the outside. I think this would solve our problems of the rocket flying out of control. But to put the connectors on the inside of the rocket, we'll have to make it larger, because it will need space for the parachute, the rocket engine, the wadding, and instead of scaling up the previous version, I'm going to completely redesign the rocket. For multiple reasons. The first reason is that I want to take away the second tube on the side, which will help reduce drag, and it's also not needed anymore, because if we have the connectors on the inside, it should be reliable enough to not explode. The second reason that I'm redesigning the rocket, instead of just scaling up the previous version, is that I'm going to make the nose cone hollow, so we can add our altimeter to the inside, instead of having to put it inside the rocket. So in CAD, I redesigned the rocket and made the nose cone hollow, and I also took away the second tube that was not needed, and now we only have a small launch lug on the side. Hopefully, this design will be better, and we've also got our interior connectors that'll hold all of the pieces together. So I finally finished printing it, but before I assembled it, I wanted to make sure that I actually explained what this rocket's made out of. The rocket is made from a white PETG, a strong 3D printer filament, and the whole rocket, without the hardware inside, weighs roughly 102 grams. The C65 rocket engine that I'm using produces a max thrust of 15.3 newtons, or 3.4 pounds. It weighs 25 grams, and the parachute that I'm using weighs 9 grams. That brings the total weight of our rocket to 136 grams. If 1 newton can lift 1 kilogram at a rate of 1 meter per second, and my rocket is 136 grams, or 0.136 kilograms, that means that we would need about 0.136 newtons of force to lift my rocket at 1 meter per second per second. That would be correct if Earth did not have gravity, but it does, so we need to account for that. For what I understand, gravity is consistently pressing roughly 9.8 newtons of force at the surface of the Earth. That means that the rocket would need to have somewhere around 9.936 newtons of force to fly at 1 meter per second. This means that we do have enough thrust to lift the rocket at 1 meter per second, and it will accelerate faster than that because we have leftover thrust. The rocket engine will fire for 1.6 seconds. If we find the acceleration divided by the force and the mass, we get 38.24 meters per second. Then, if we multiply the acceleration by the time that the rocket engine fires, we get 61.184 meters. So I finally launched that rocket, and it didn't go all that great. The rocket launched pretty well and went almost straight up, but in the middle of the flight it turned about 90 degrees and shot off really far into the woods, and I wasn't able to find it. So I decided to print the same model of rocket again, and I launched it and almost the exact same thing happened. So I plan to, in the next rocket, incorporate Thrust Vector Control Systems, or TVC, and I'll talk about that in another video. Hopefully this new plan works, and if it does, I'll see you in the next video.